Hi everyone, welcome to Learning Math with VK. Today we explore lesson 32 in algebra, applications in exponential growth and radioactive decay. 1. Application in exponential growth. A population of 10 bacteria doubles its size every half hour. Find a function to model the population of the bacteria culture. Then model the population of the bacteria using the natural base E. To do this one, let's take a look at a little table. Time, population. After half an hour, population is double, 10 times 2. After 1 hour, gonna double again to 10 times 2 times 2. 1.5 hour, 10 times 2 times 2 times 2. 2 hours, 10 times 2 times 2 times 2 times 2. Okay, let's see a pattern here. Well, we only care about after each hour. So after 1 hour, we have 10 times 2 square. After 2 hours, 10 times 2 to the power 4, which is the same as 10 times 2 to the power 2 times 2. And 10 times 2 square is the same as 10 times 2 to the power 2 times 1. Now, after 3 hours, using this one, it will be 10 times 2 to the power 2 times 3. Nice pattern, huh? And then after 3 hours, then we would get 10 times 2 to the power 2 times t. So that means the formula here is population is pt equal 10 times 2 to the power 2t. Very cool formula. We can also use base E, right? The base here is 2. Where we use the base E, using base E, then PT would be 10 times E. Well, it will no longer be to the power 2t. It's going to be some power KT. We need to solve for K. We can use the table here. So let's use population after 1 hour. What does that mean? It means that P1 population after 1 hour is 10 times 2 square, which is 40. We're gonna use it. And what we do here is that we're gonna do the sub. Forty is equal to 10 E K times 1. So divide both sides by 10, we have EK equal 4. And then ta-da! Can get rid of E, taking L1 on both sides. We have K equal L1 4. L1 4, punch it in the calculator, is 1.3863. So the model using base E is gonna be PT equal to 10 e to the 1.3863 t. Let's graph them in decimals, and you see that they are the same. Okay. One model is the 10 times 2 to the power 2t. Instead of using 2t, I'm going to use 2x there. Another model is the 10 e to the power 1.383 t x. They're the same graph. Pretty cool, huh? Okay, let's move on to the second application. Application in radioactive decay. First example, how long will it take for a sample of H3 to lose 70% of its original amount? Consider the half-life HL of H3 is 12.26 years. You got to do the table. Half-life, that will be the age. Amount remaining. One half-life, half of the original amount, let's say A sub 0. Two half-life, the remaining is going to be half of the original amount, which is 1/2 square A sub 0. Three half-life, half of half square A sub 0. So this half to the power 3 A sub 0. And then eventually we get n half-life. And we have 1/2 to the power n A sub 0. From the table, we see that amount remaining equal to half to the power n of the original amount. Nice formula. Let's use it. Okay. Look at the problem. Lose 70% of its original amount. That means 30% of the original amount remain. So 30% of the original amount remain. Amount remaining 30% of the original amount equal 1/2 to the power n A sub 0. From here, we can divide both sides by A sub 0. And we have 30% is 0.3 equal 1/2 to the power n. We need to solve for n. So take ln both sides, ln 0.3 is n ln 1/2. From here we see that n is ln 0.3 divided by ln 1/2. Each is n half-life. We know n is ln 0.3 over ln 1/2. Half-life is 12.26. Plug this in the calculator. Then the age is 21.30 years. Cool, huh? Let's go to the next example. An artifact contains 40% of its carbon-14. How long ago was it made, given the fact that half-life of carbon-14 is 5,730 years? Let's use the formula. Amount remaining equal half to the power n of the original amount, a sub 0. Amount remaining is 40%, so that is 40% of the original amount is half to the power n, a sub 0. Divide both sides by a sub 0, get rid of it. So we have a 0.4 equal 1/2 to the power n. And then from here, we can figure out n, take ln on both sides, ln 0.4 is n, ln 1/2. So it means n is ln 0.4 over ln 1/2. To find the age, we use the formula h is n half-life. We know n ln 0.4 over ln 1/2. We know the half-life 5730. Plug this in the calculator and we have 74.65, which is approximately 75 years of age. Pretty cool, huh? Last example. A 32 grams of radioactive substance decays to 17 grams after 60 minutes. 5 is half-life. To do this one, we use two formulas. The first one is amount remaining equal half to the power n of the original amount, a sub 0. Amount remaining 17 grams, half to the n times 32. Divide both sides by 32. 17 over 32 equal half to the power n. Take ln on both sides. We have ln 17 over 32 equal n ln 1/2. Divide both sides by ln 1/2 and ta-da, we have n to be ln 17 over 32 over ln 1/2, which is 0.913. Next, we're gonna be using the age formula. Age is n half-life. The radioactive substance decay to 17 grams after 60 minutes. So the age here is 60 minutes. We know n 0.913. We don't know the half-life. So from here, we can divide both sides by 0.913 and the half-life is 60 over 0.913. Half-life 65.72 minutes. Thank you for watching. I hope you find the content useful. Please like and subscribe to help the channel growth. I'll see you in the next video.